All right. Ladies and gentlemen, whether you like it or not, recording has started. So, as we discussed briefly previously, tomorrow, test over the whole circular motion idea, and we'll get into the details of that as we go along. Okay? What planned for today, I wanted to go through topics that we've covered, problem sets that we've done, where you can find answers, what you can do to help yourself get ready for test, etc., etc., etc. So, starting off, this unit started back on April 16th with the introduction to centripetal acceleration and centripetal force. So we talked about the idea that something moving in a circular path is accelerating because of the whole changing direction idea. And because it's accelerating, it needs to experience, or it's experiencing acceleration, but because it's accelerating, it needs to be experiencing a force. And we call that acceleration centripetal acceleration, and we call that force centripetal force. And we talked a couple of things about the orientation of those things. What do we know about the orientation of centripetal acceleration and centripetal force? How are they directed? Towards the center of whatever our circle is that we're going around. Also, we talked about how it's oriented to something else as well. How is it related to the current velocity of that object? It is perpendicular to the velocity. So the velocity, its inertia, is telling you to go one way. The force, or the cause of the change, is telling you to go in another way that's at a right angle. The end result being, if something is trying to tell you to go straight, and something else is trying to tell you to go towards the middle, the end result being you go somewhere in between those two. Right? And that's where we get the circular path from. As far as the values for centripetal force and centripetal acceleration, two formulas that ended up on the board, right? Or ended up on the wall. So the centripetal acceleration, we said, was equal to v squared over r. What did we say the v represented? The tangential speed, right? Which is kind of like velocity. Tangential speed is measured in meters per second. It's how fast are we traveling around the outside edge of that circular path. And we also talked about a couple of ways to calculate this, right? How can we calculate the tangential speed of an object? If we take its circumference, 2 pi r, and divide it by the period, the time of one rotation, that will give us the meters per second that we're looking for. Circumference being measured in meters, period being measured in seconds. And then that takes us care of the v value, right? And then
so the tangential speed, like it equals v, but like you substitute it for v squared, like you don't square that value, or do you?
So Rachel, when we calculate this, right? This, whatever we get out of that calculation goes in for v. So the answer to that problem we will square.
Okay.
Yeah.
So if on a question it's like, oh, the tangential speed is 5, then would you make it 25?
Well, if you're calculating when you plug, 5 would go in for v. V gets squared in this formula. Yeah. So, but then with this, like this, you should get a value out of that. You should get a number when you do that calculation. Then that number can go in for this v, and then you just square it. And then r, when we're talking about circular things, is just going to be what? The radius. The centripetal acceleration needs to be caused by something. That something being the centripetal force, F of c. In order to calculate the centripetal force, we need to know 3 things. We need to know the mass of the object that's moving around in a circle. We need to know the tangential speed, and then we need to know the radius of the turn that we're going around. Good with these two formulas? The first problem set I gave you in this section was this one. It says Intro to Centripetal Acceleration and Centripetal Force. And on this problem set, The first side was very conceptual, talking about the things that influence centripetal acceleration and influence centripetal force, how they influence those things. And then the back side were some sample calculations. Calculating centripetal force, calculating centripetal acceleration. Okay? One thing to keep in mind, we've done this a couple of times throughout this section, but there are different ways of representing tangential speed. On this problem set, in number 7, it gave you a tangential speed in revolutions per minute. We can't have tangential speed in revolutions per minute. It's got to be meters per second. So you have to do a little conversion there, right? Converting the minutes, well, hopefully, right, if you get this, if you get a section like this, or if you get a problem like this, that gives you a speed in revolutions per minute, start it off like this, right? 12,000 revolutions over 1 minute. And when we're all said and done, it's got to be in meters per second to give us the tangential velocity. So set yourself up a couple of conversion factors. First conversion factor, we'll go minutes on the top, seconds on the bottom. That gets rid of our minutes unit, right? It leaves us with seconds on the bottom, which is what we need for tangential speed. And then for this, we can go revolutions on the bottom because they have to cancel the revolutions on the top, and we want meters here. All right? That, and then the circumference being the distance of one revolution. So if I give you a speed in revolutions per minute, you've got to make sure we convert that into meters per second. It's out of garbage.
I was going through the
Oh, okay. Fair enough. All right. Good there? You also took a quiz over this section here, which if you have not, if you don't have it, it should be over in the bottom tray over there. Good on intro stuff. The last week and a half of this unit, starting on Friday, April 20th, dealt with problems. One of the things that we said about centripetal force was, centripetal force is not some standalone kind of force. It has to come from somewhere. Okay? Some other force that we've talked about has to provide that centripetal force. And the next week and a half dealt with, okay, where's the centripetal force coming from in this section or in this situation? Where's the centripetal force coming from in this situation? That started with this problem set that said calculating centripetal force, friction, bank turns, and tension. And there were 3 different types of problems on there. Each of those different types of problems always started the same way. It always started with f of c equals something. The first set of problems that we did, we talked about that f of c, the centripetal force, was provided by some frictional force. And we did some calculations where we drew a cool picture of looking at a car from the front, right? Remember that? Yeah. Okay. Totally cool. Totally cool. I mean, I'm pretty sure I recorded some, so you can go back and take a look. But anyway, when we do this, right, this being the first kind of problem where centripetal force coming from the static friction force, on centripetal force side, what are we pretty much always going to substitute in over there? On the centripetal force side, what's going to go over here on the left-hand side of this equation? mv squared over r is going to go over here. And then, for the frictional force, right, we could rearrange this formula, right, to solve for the static friction max. Or, if it's asking you to solve for the coefficient of friction, if you solve this equation, right, where you know that friction is providing the centripetal force, you can use the answer to this and then plug it in the coefficient formula to solve for the coefficient. Okay? Which is what we did in the, if you did the record player the other day, where you solve for the coefficient of friction between the object and the record player, that's pretty much what you had to do in that case.
So you could take mv squared divided by r and put it in for the max.
Yeah. Okay. Or Jesse, on a like that's did you do the record player problem the other day?
I don't think so.
Okay. That's what we did in the record player problem, where you know that friction is providing the centripetal force to that thing that's sitting and spinning around in a circle. Okay? You know that the centripetal force that is required for an object to spin in a circle is equal to this much. So you know if there's this much centripetal force and it's coming from friction, if I find the value of mv squared over r, I know the frictional force. Then I can plug it in over here, find what we need. Or another problem that we did, like with a car going around a turn. I think the very first problem that we did was how fast could a car go around a turn if the coefficient of friction is such and such. Okay? So in that case, we're solving for this value. Actually, we're solving just for the v, not v squared, but okay. We're solving for this value. If I know the coefficient of friction and I know the normal force, I can figure out the max static friction. Then I can take that answer and plug it over here. Does that make sense?
Yeah.
So it kind of depends on what you're looking for in that situation.
Okay.
Good with that? Answers to those frictional problems are posted on the website, right? On the 20th of April. It says answers to centripetal force friction problems. There's also a link there. It says class reporting of sample problems from class. So I think we did 2 examples in class. You can go through it and see how we did it. Check it out. Yeah. Questions? Okay. Next type of problem that we did was the banked turn problem. The banked turn. So we talked about the idea that if we actually tilt the road gets in the way of that object going straight, and the normal force, or a portion of the normal force, will provide centripetal force. Let's grab this picture here. So, JT, we talked about this in class, that in this case here, we technically don't need a frictional force if our angle is banked well enough. We said that there were 2 forces acting on this car. There's a gravitational force this way, and then there's a gravitational force that way, and then there's a normal force. But in this case, because the road is not flat, the normal force is not straight up. If it's not straight up and down, what does that mean about the normal force? It's got components. And there's a component this way, and then there's a component this way. Okay. In this picture, you can see that as this car is going around this bank turn, it's moving at least partially on a circle where this is the center of rotation. Which means this component, which is pointing horizontally, also points towards where? Center of the circle. And that means that this component can provide the centripetal force. This component being the horizontal component of the normal force, Fnx, because it's on the x-axis. An important thing that we discussed: if this road is banked at a certain angle theta, that same angle theta will show up in this picture right there. Right? It shows up between the actual normal force, the solid blue arrow, and the vertical component of the normal force. In this case, if these are the only 2 forces that are acting on this object, what did we say about the vertical component of this triangle? It's going to be the same as gravity. If those are the only 2 forces on the y-axis, and this object is turning on the x-axis, those two, the vertical component of the normal force and the gravitational force have to be the same. So in that case, if I can find the two sides of this triangle, I can find that angle theta, right? Or if it gives me angle theta, and I know that the vertical component has to be equal to gravity, now I can use trig functions and find out what this side of the triangle is, and then I can plug that answer into here and solve for V or R or whatever it is. Okay? Good there? We did a couple problems like that in class. Okay? Monday, April 23rd, bank turns 1 and 2. Answers to bank turn problems from your problem set. Also, on Wednesday of that week, Wednesday the 25th, we did a couple of problems, extra problems that I gave you in class. And they look like this. I gave you a couple of slides in class, and there was 4 of them, 2 on the front side, 2 on the back side. 2 of them were bank turn problems. The other 2 problems were tension problems. Okay, so let's talk about tension. So we said tension is just a fancy name for a force coming from a string, right? And it can do exactly the same thing as bank turn can do, or it can do the same thing friction can do. On the problems that I gave you on Wednesday, the supplemental sheet that had the 2 on the front, 2 on the back, a lot of the tension problems looked very much like bank turn problems, where the angles were similar. Okay? But the one thing that made it different was the third problem set that I gave you, which was called Calculating Centripetal Force, Vertical Circular Path. So when we start talking about something moving up and down as it's going in a circle. Alright, so here's this girl, and she's going to let this bowling ball go, and it's going to go in a circular path.
It's going to break the rope.
What?
The rope's going to break.
No, absolutely not. Alright, so let's see if I can do this without making a huge mess. Nope. Apparently not. Okay, so there's the circle, or at least part of the circle that it's going to travel on, right? She lets this pendulum go, it's going to swing along here, it's going to stop here, it's going to come back. But that time, it's moving along a circular path, which means it has to have centripetal force. The one spot that we're really concerned with is this spot down here. At that point in time, the very bottom, we said there were 2 forces that were acting on that object, right? What did we say the 2 forces were acting on the object at that point?
Gravity.
Yeah, gravity. And that's going this way, right? But there's also this tension force, the force coming from the string. The important thing about the tension force being that it points which way?
Up.
Towards the middle. Points up, yes, but more importantly in terms of the circle, points towards the middle. So we said that in this case here, this object still has to have a centripetal force. But that centripetal force is now a combination of 2 things. In this case, right, which way is f of g pointing in relation to the circle? Outward, right? So we said, what did we do with that in that case? We made that negative, right? So it really looks something like this. Does that sound remotely familiar, hopefully? The one other kind of, so vertical circle, where gravity is sometimes helping, or sorry, gravity is sometimes hurting, but we also talked about the idea that it's probably a lot of work for what it's going to be worth, but that's okay. That's when our object gets up here, right? It's the same gravitational force acting on it. But now, which way is it pointing?
Towards the
Down, but in relation to the circle, towards the center. So that means that the centripetal force is still made up of two forces. But now, which way is the gravitational force? It's pointing towards the center, so do we subtract it in this problem? No, we'll give that a positive one. So that means that the tension force becomes smaller because it doesn't have to do as much work in that case. Or it doesn't have to provide as great of a force. I shouldn't use work because it has an actual definition. Is it possible that the gravitational force can provide all of the centripetal force up at the top of that motion? If we go here, right, we'll substitute mv squared over r, right? Okay. F of g I can't change. If f of g just so happens to be the correct amount of force that you need to do the centripetal force, does the tension do anything at that point in time? Doesn't. Good there? Last kind of problem that we did on Friday dealt with apparent weight. Okay. At the bottom of the Ferris wheel, this person has a gravitational force that looks like this. And then it has a normal force from the seat that looks like this. Actually, it looks more like that. But, yeah. So, we talked about here F of C, a combination of these two forces, right? The normal force being the blue, gravitational force being the green. But once again, which way is gravitational force pointing in this problem? Down in relation to the circle,
outward.
out of the circle. So this problem would look something like this. And how would the normal force compare to if you were just standing on the ground without moving in a circular path? As I'm passing through the bottom of this circle, if I'm just standing on the ground, how does my normal force compare to my gravitational force?
Equal.
They're equal, right? But am I accelerating in this case? No. As I pass through the bottom of this Ferris wheel, am I accelerating? Yes, because what path am I going in? Circular path, right? So there has to be some acceleration. So can the gravitational force and the normal force be the same as each other? Can't be. Okay? In this case here, which way am I going to start going as I'm passing through the bottom here? I'm going to start going back in an upwards direction. So how does normal force compare to gravitational force in this case?
Bigger.
Got to be bigger. Well done, Farrell. Well done.
Yeah.
So we said in this case here, you have an increased apparent weight. We said that's when you go through, excuse me, that's when you go through the bottom that's when you go through like the bottom of a roller coaster and you get that sensation like you're kind of getting pushed down into your seat. Okay? But up at the top, the person is still feeling that same gravitational force. And there's still a normal force. Can that normal force still be bigger than the gravitational force at that point in time?
No.
If it was, which way would that person start moving? Upwards, and that doesn't happen. So how is the normal force have to compare to the gravitational force in this case? It has to be smaller, right? So up at the top, that normal force is decreased. To solve the problem, you're still going F of C is equal to F of G plus F of N. I had it written backwards or the other way down here. It doesn't really matter. Okay? But in this case, which way does F of N point? Away from the circle. So Two things. One, because it's negative, it's got to point out of the circle. Two, how would it now compare to the gravitational force? It's got to be smaller. And then we say that F of n, or the apparent weight, is less up at the top of that because of the idea that the normal force doesn't push on you quite as hard. And we said that's that sensation of the roller coaster when you're going over the hill. You get that sort of like floaty feeling as you're going over the top.
So the difference between this and the last one is just the fact that you have like the seat under you, so you can't.
Right. Whereas Jesse, like in this problem, tension's always going towards the middle. In this problem, it just either gets bigger or smaller.
Yeah.
Here, it's still, the normal force still gets bigger or smaller, but sometimes it's pointing away and sometimes it's pointing towards. And that's where you get those different sensations of apparent weight.
Okay.
Okay? We said this, the whole idea here is the idea of apparent weights. And we talked about on Friday, if the problem is asking you to solve for apparent weight, what is it really just asking you for? If it says, what's the apparent weight at this point, what's the apparent weight at that point, it's just asking you for the normal force. It says, what's the normal force at this point? Questions? So you have multiple problem sets to work through. Answers to all of those problem sets are posted online, going all the way back to the friction problems, the bank turn, the tension, then the apparent weight and the vertical circle problems. I think you have a total of 5 problem sets that I've given you over the past week and a half or so. Okay? If you have questions, come see me before school. I have a meeting before school tomorrow, but come see me before then. We'll figure something out. Okay?
Are you gonna post the slides too?
These?
Yeah.
I can if you want.
Yeah.